Allie, the title of this lesson is Power and Efficiency. I'm going to skip efficiency. I'm just going to give you a Reader's Digest condensed version of what efficiency is. Efficiency is how much energy is lost. The more efficient an object is, the more of the initial energy that you started with went into performing a useful task. The less efficient an object is, the more wasted energy there is, usually in the form of heat and sound. Okay? Power. The word power is used in a variety of ways in everyday language, but in physics it has a very specific meaning. Power is the rate at which work is done. In other words, power is work divided by time. It's how fast you're transforming energy from one form to another. If you're doing it faster, you're generating more power. Same amount of work. Just from, it's a scalar? Well, of course it's a scalar, because work is a scalar and time is a scalar, and a scalar divided by a scalar, there is no direction, much like your future. Anyways, it's got to be a scalar. What are the units for power? Well, first of all, what are the units for work? Per. But power is such an important concept, we've given the joule per second a name. Power is measured in what? Power is measured in what? In watts. Symbol capital W. By the way, here's where we're going to run into a little bit of a problem, because now we're in a unit, a topic, where work, W is work, but W next to a number, to the right of a number, is watts, where you're going to see W's appearing with different meanings in your same question. Just be careful. I've gone on my rant about how we don't have enough letters in the English alphabet. Yeah, okay. Making sure I'd said that at least once before. Oh, and also W is west. Thankfully, that won't be too much of an issue because it's a scalar, as is work and energy. So we shouldn't run into 3 W's in the same question, I hope. Karen, imagine again walking upstairs versus running upstairs. If you're expending energy, it's not how much work you do that makes you feel tired. It's how fast you do the work, or how much power your body is generating. Work is not what leads to tiredness. Power is tiredness. If you ask me in physics, what makes you tired? You're generating a lot of power. And by the way, this is how stairs and ramps work. The shallower the stair, the easier it is for somebody to walk up. It'll take you longer. You'll do the same amount of work versus climbing a ladder. Same amount of work, but you're doing it quicker, more tiring. So you expend the same amount of energy, would be mgh, but a ramp or a stair lets you take more time, so you feel less fatigue. Okay? That back corner stairwell in our field is a classic example. They've clearly built that fairly shallow because they recognize it's not just high school kids who are in pretty good shape using it. Senior citizens are going to want to access the field and go for a little walk. In fact, it's so shallow, it's awkward for those of you that are in good shape. Yes? Because it's just awkward to walk on at speed. Sprinting on it is really awkward. So you almost have to slow down because you almost got to do 2 steps per stair on that thing. Kind of. No. Is that one? No, that's got just some long ones and some normal stairs. It's a different stairwell that has the longer stairs, right? That back one, though, is weird, is it not? I think I'm thinking of the right stairwell. Yeah, sometimes they make stairways which are so badly designed, you just, I've got to do 2 steps on each stair because I can't stretch my legs far enough because the treads are just really, really long or whatever. A young girl runs up a flight of stairs 3.32 meters high in 2.6 seconds. What's her power output in watts? Okay. McKenna, what's this question asked me to find? What is her? So I'm going to start out by writing power. Power is capital P, lowercase p is something else, is W over T. And I'm pretty sure the time is 2.6 seconds. That's kind of obvious. What about her work? Anytime you're climbing or lifting or anything against gravity, that's going to be mgh. It's the change in potential energy. And started on the ground, so what's our initial potential energy? Our initial height is 0, so our initial potential energy is 0. So I got really sloppy. I didn't even write the delta. It's just going to be mg times your final height. Okay, 60 times 9.8 times 3.32 divided by 2.6. One of you did forget the 9.8s on the forces test in one question, by the way. You wrote them all, you wrote the G's all the way down, and then as soon as you started to write out the numbers, the 9.8s vanished. Told you. What do you got? $751 Okay. 3.32 meters. That's almost bang on this stairwell in the back corner there. 2.6 seconds. You're hustling, probably jogging up the stairs, not walking. Could all of you do that? Yes. In other words, are all of you capable of generating about 750 watts? Yep. Some of you more. Not necessarily for a long time, because eventually you get tired and you got to rest. Okay? If 1 horsepower equals 700, the imperial unit for power is horsepower. If 1 horsepower equals 750 watts, what's her power output in horsepower? Almost exactly 1 horsepower. Most of you can put out a little more than 1 horsepower for a fairly extended time. And by extended, probably most of you can jog like that for 10 minutes or so before having to rest. Okay. This would be on that running up the stairs like that. On the exertion scale, probably about a 6.5 out of 10 or a 7 out of 10. So you would eventually have to rest. Horsepower was originally invented by James Watt. The Watt is named after James Watt. This is one of my big beefs. I think James Watt is overrated. And especially because the watt is such an important unit in our current lifestyle because it shows up in electricity as well. Light bulbs are measured in watts. I don't think he should have a unit named after him, but we do. The horsepower is also a big joke. James Watt improved the steam engine. Some people will say, oh, he invented the steam engine. He improved it, but what he really was, Aiden, was a good salesman. He wanted to convince farmers and factory workers to replace human beings or horses with his steam engine. And so he invented a unit called the horsepower. That is not how much work a horse can do, but when he tells a farmer this steam engine is 4 horsepower, what does the farmer think? Immediately, this will do the work of? It was such a brilliant unit advertising scheme that we still use it today. Nobody knows today how much work a horse can do in a day. It's nonsense, but we still measure engines and horsepower. That's a pretty brilliant ad pitch right there. That was really his best move. Example 2. How long would it take a 5 horsepower motor to lift a 500 kilogram safe up to a window 30 meters above the ground? Aiden, what's this question asking me to find? Yes. Did we just have an equation with time in it? Power equals work over time. Aiden, where is the T in this equation right now? On the? Ugh. Oh, no. Times it to the top. And then how could I move power to the other side? Yep. Another equation for time, and it's not like we don't have a gazillion equations for time already, but another one apparently is the work done divided by the power usage. Everybody underline the word lift. When we're lifting something against gravity, how do we calculate how much work that is? Yeah, mgh. So the top of this equation is going to be mgh. The bottom, why can't I use that 5 horsepower? We're in the metric system, the SI system. So I'm going to make a little note here. Power equals 5 horsepower. I guess I want horsepower to cancel, so it's going to go on the bottom. I want watts on the top. See how I'm using dimensional analysis from last year? And what's my conversion factor? Apparently 750 watts is 1 horsepower. Am I going to times by 750 or divide by 750? How do I know times? Because the 750 is on the top. How many watts of power is a 5 horsepower engine? I can probably do this in my head. 750 times 2 is 1 times 4 is, so it's going to be 3,750? So it's going to be 500, don't forget the 9.8, 30 divided by 3,750. How long will it take? Marcus, what'd you get? 39.2. What if you want this safe to go up faster? It's impossible. You need a bigger engine, more horsepower. Now, this is kind of a whatever, but replace 5 horsepower with, you know, the big building cranes, those trellis ones that slowly build up and up on skyscrapers. You can make a pretty accurate prediction in terms of calculating how much mass you're going to need to be lifting to build the building for each floor. You can make a pretty accurate prediction as to how much time it's going to take you on the crane portion to do that. It's a pretty trivial calculation, so they can be pretty accurate. How much physical time will we need just to lift these objects up? Oh, you want to get it done faster? Get a bigger crane. Of course, that costs more money. So, okay. There's another definition of power. So power is work over time. I gave you that one on your formula sheet, I think. I know I did, right? Where's power? There it is. But you can also rewrite it as power. Work is force times distance. And so, if I circle the D and the T, what do I measure distance in? Meters? What do I measure time in? What is meters per second a measure of? Another way to calculate power is if you have constant force times constant speed. Mr. Dewick, how can you have a constant force and a constant speed? Wouldn't you be speeding up? We're assuming there's another force canceling out your force. A great example, how many of you on your bike have ever pedaled as fast as you possibly can and tried just to see how fast you can go? Okay, that maximum speed, it's limited by how much power you can generate and air resistance, because air resistance is what's canceling out your force from the pedals. When you match air resistance with your maximum force and your maximum power, you could actually solve for that's your maximum speed that you can get the bike to. Okay. In Physics 11, we do that. This is why I'm kind of kicking myself. I should have used my Physics 11 notes. I calculated. Physics 12, I didn't include that here, and well, whatever. But that's okay. Efficiency is how much bang we get for our buck. If you put in 1,000 joules of energy and you only get out 800 joules of work, that's 80% efficient. There's the explanation. Skip that. Skip that. Example 4. A mass of 100 kilograms is pushed along the floor at a constant speed. If the coefficient of kinetic friction is 0.25, what's the power output? Ariana, what's this question asking me to find? Now, my first thought was to go work over time. Do you see a time in here anywhere? Do you see a speed? And I think I gave you this definition of power on your formula sheet as well. I'm going to go force times speed. Which force? Don't know. Oh, Ariana, did they give me a coefficient of friction in this question? What might this be a good job for? I think over here, I'm going to draw, just to get a visualization, a free body diagram. What are the forces acting on this object? Get the obvious one. What else? Are we sinking in the ground like quicksand? So normal force? Yes. Is there friction? Let's point it to the left. Why is this diagram impossible based on what they've told me? Yeah. Same size, yes? What force is that? I guess that's the mystery applied force. And that's technically what's going to go there. I don't know the applied force. Oh, but look. I know another force that has to be the same size as the applied force. What? Yeah? Power is going to be the force of friction times speed. So I got to be fussy, McKenna. I'm not saying in this case power is friction times speed. I'm just saying, you know what? The force that I'm pushing at, it's got to be the same size as friction. So why don't I calculate that magnitude and put it in there? Friction is mu times the, I don't know the normal force. Oh, but look. I know another force the same size as a normal force. What? So I think I can say mu mgv. That's how much power any of you would be generating if you were sliding an object across a rough floor at a constant speed. Notice, if you want to make it go faster, how can you make it go faster? You've got to generate more power. You're going to get more tired, which again is kind of stupidly obvious. Well, yeah, if I'm pushing it faster. When those gym benches, if I sprint them across the gym, I'm huffing and puffing. But it's nice to know that the physics works for that, Karn, is all I'm saying. It's going to be 0.25 times 100 times 9.8 times 2. I might be able to do that in my head. Sure. 100 times 2 is 200. 0.25 times 200 is 50. 50 times 490? Units. Power is measured in watt? Normally I would do example 5 because it's a nice review of lawnmower questions, but I'm cutting corners. Normally I would do example 6 because it's a nice review of lawnmower questions, but I'm cutting corners. Okay. Stair climbers. This question mentions efficiency. I'm going to skip the efficiency portion, so we're going to skip part B. Part A says, find the rate at which the person does work. What's a physics synonym for the rate at which an object or a person does work? Starts with letter P. Power. This is saying find the power. Karn, do you see a speed anywhere in this question? No. But you know what word I do see? Lifts. I think it's going to be potential energy. You know what? I'm going to use the work over time version of power, not the force times speed version of power. In fact, lifts, how do we calculate how much work you're doing? MGH over time. There's a number that I don't like in this question. Can you see it? Yeah. In fact, what I should have done is right away crossed that out and said 0.22 meters. Nice try, Mr. Dewick. There's another number I don't like in this question. Minutes. I should have crossed that out. 6 minutes. How many seconds? Times by 60? Is it? Yeah. So 360 seconds. Okay. Let's keep going. M. Oh, 75. G, 9.8. What's the height? It's not 0.22. What's the height that this person is climbing? Why isn't it not 0.22? Oh, 360 times of those? Okay, so 360 times 0.22, gotcha. Divided by time, 360. So if you've ever used an exercise machine and the exercise machine is telling you how many calories you've burned in a given amount of time, this is the calculation that it's using, because calories are actually another way to measure energy, work. So it would take the time. Oh, if I wanted to figure out work, power times time. What do you get, first of all? 153? 162? Now here's the problem with those exercise machines. Did we need this person's mass to do an accurate calculation? Yes. Do exercise machines ask you to enter your mass? Please, all of those displays on exercise machines are nonsense. And even this is nonsense, because this tells us how much power the person generated. It doesn't tell us how much energy they burned, because they gave off a lot of heat. Really, if we knew how efficient their muscles were, then we could work our way backwards and we could say, okay, if they did this much work output, how much input did they have to put in? How much energy went into heat? And exercise machines do none of that. So I'm just saying, if you use an exercise machine and you're someone who, oh, there, I've burned 360 calories because that's what it says. No, no, no. Even if you did input your mass, no. You've outputted 360 calories, but you probably burned more. So, just saying. Okay. Power is measured in watt. Power is work over time, or force times speed. What's your homework? Can you get out the ultimate review, please? I'm going to tell you which questions are fair game, and this is going to be your homework. What I mean by fair game, I'm going to make up your test probably this weekend. I'm not going to make it heavy. Definitely going to lean towards roller coasters. I'm telling you that right now. I may or may not put a power question on there as well. If I can find a question involving power that's fairly straightforward and interesting with any weird stuff, because I'm not going to throw weird stuff at you. Normally I throw one nasty multiple choice. I'm crossing that off this time because, Aiden, I have not nailed this unit. I just have not. I'm almost embarrassed. I can teach better than this, and I will next quarter. Not that any of you will see that. So from the ultimate review, I already gave you some questions to circle, yes? Did we circle number 2 or not? I'll add number 2. 3 is good, if I didn't circle that already. I can now add number 4, power. Okay. Did I circle 5 last time? Good, skip 5. Did I circle 6 last time? I did? Well, I guess there they give you all the numbers. You know what? I'm going to cross out 6. I don't like the way it's worded after all. Okay. 7 is okay. 7 wants you to find power. You'll have to figure out the work. Oh, work is the change in kinetic energy. Did they give you the final kinetic energy? Did they give you the initial kinetic energy? They've done that for you. Thank you very much. So 7 is okay. Did I give you 8? Okay. And the reason is, here he's got 9,700 joules of energy. It's all kinetic. How much will be kinetic up there? So what will that 9,700 have changed into? MgH, sulfur H. Okay, so 8 is fair game. Did I give you 9? I shouldn't have. Did I give you 9 last time? Okay. By the way, Cleo, this number 9 is the same question you asked me number 15, in that it's asking you to find the mass. Here's how much work was done, this whole area. Oh, and you'll let that equal a half mv squared, but instead of getting the v by itself, you'll get the m by itself. But nah, I'm going to say 9. Did I give you 10? Yeah. Asking you for its kinetic energy. Really, it's saying how much work. It's the area underneath that triangle. 11 is good. I gave you 12 last time, yes? Yep. Definitely would have given you 13 last time. Roller coaster. Okay. So here is an example of a roller coaster, and this time they're asking us to include heat. My handwritten answer key is on Pit Math. You can always check. Skip 14. Skip 15. Skip 16. Did I give you 16 last time? I did? No, good. Skip 17. Skip 18. Skip 19. Did I give you 20 last time? I probably did. Skip 21. 22 is fair game. Did I give you that last time? I should have. Good. Skip 23. Skip 24. Did I give you 24 last time? Okay. Skip 25. Sure. Well, for 26, assume you're on level ground. So when it says find the speed, you're going to find the change. The work is this area, and that's the change in potential plus change in kinetic. Assume change in potential is 0. So I don't like the way this question is worded. Should say over level ground in my mind. But I'll give it to you. Skip 27. 28's good. 29's good. Skip 30. Skip 31. 32 is okay. $33 is okay. Yep. $34 is a little too tough. Did I sign 34 last time? No? Okay, good. Skip 35, skip 36. $37 you can do. You'll just have to figure out the force, but they gave you a mass and you can figure out A. And then it's going to be force times distance over time. I think you can do 37. Skip 38. 38's nasty. Skip 39, lawnmower. Skip 40. Scholarship questions, skip 41. Skip 42. I think I'm going to do that. Now, are there any more roller coaster-y questions that are worth practicing, Mr.? I gave you a bunch of roller coaster questions, I think, in the homework. So I think you've had some of those to practice. So, which one, Noah? I don't know. Let me go look. 33 and 34? I circled 33 and I skipped 34. So you would have had a 50-50 chance of being correct there. Okay. I apologize, but with the late start, I'm going to sneak in one more short lesson that just kind of isn't part of this unit. It could go anywhere, but it's graphing tricks, which are handy, and they might help you in your math courses too.